Ladies and gentlemen, today we'll be delving into a fascinating experiment that shaped our understanding of atomic structure. This experiment involved the scattering of alpha particles by a thin gold foil, revealing insights that were groundbreaking for the field of physics. Let's explore 7 key points about this experiment and its profound implications. In the groundbreaking experiment, a stream of alpha particles, which are helium nuclei consisting of 2 protons and 2 neutrons, was directed toward a thin sheet of gold. The source of these alpha particles was a radioactive material, typically radium, which emitted them with a specific energy level. This energy allowed the alpha particles to travel through the air and interact with the gold foil. The choice of gold was crucial, as it is a dense, malleable metal that could be hammered into an extremely thin sheet, about 1,000 atoms thick, ensuring that the particles could interact with it more effectively. The setup also included a detection system, composed of a fluorescent screen coated with a material that would produce flashes of light when struck by the alpha particles. Surrounding this screen was a microscope, which allowed researchers to precisely observe the locations of these flashes. The screen was arranged in a circular manner around the gold foil so that it could detect alpha particles that were scattered at various angles after they interacted with the gold atoms. The experiment was conducted in a vacuum chamber to minimize the influence of air particles that could deflect or scatter the alpha particles before they reached the gold foil. This ensured that the results were not affected by external factors and the particles traveled unimpeded to the target. The alpha particles were emitted in a very narrow beam, ensuring that they hit the gold foil at various angles and allowed for accurate measurement of how they scattered upon contact. The apparatus was designed to detect even the faintest scattering events, enabling the team to measure the angles at which the alpha particles were deflected. The screen and microscope setup was sensitive enough to reveal particles that had been deflected by as little as a few degrees, all the way up to those that bounced back almost directly along their incoming path. This sensitivity was key to revealing the unexpected nature of the results, specifically the large angle deflections that had not been anticipated based on earlier atomic models. The experiment's setup was not only precise but also innovative. It required an understanding of both the nature of alpha particles and the design of sophisticated detection instruments. The arrangement ensured that the experiment was not influenced by background noise or interference, which allowed for the discovery of key results that would later transform the field of atomic physics. It's important to note that this experimental setup was quite different from what had been used in previous atomic models. The use of alpha particles, combined with a gold foil target and precise detectors, allowed scientists to directly probe the structure of atoms in a way that had not been possible before. The relatively simple yet highly effective setup thus provided the perfect means to investigate the previously mysterious inner workings of the atom. In essence, the experimental design played a critical role in revealing the structure of the atom. Without such a meticulously planned and executed setup, the critical observations about the nature of atomic nuclei, especially their small size and dense positive charge, would have remained undiscovered. The attention to detail in the design of the equipment, the choice of materials, and the sensitivity of the detectors were all factors that contributed to the success of the experiment and its lasting impact on the development of atomic theory. The results of the experiment were completely unexpected and contradicted the existing theories of atomic structure at the time. Based on the prevailing atomic model, it was anticipated that most of the alpha particles would pass through the gold foil with little to no deviation. This assumption stemmed from the plum pudding model of the atom, which proposed that atoms were composed of a diffuse cloud of positive charge with negatively charged electrons embedded within it. In this model, the positive charge was thought to be spread out, meaning that the alpha particles, which are also positively charged, should experience only minimal repulsion as they pass through. However, the results did not align with these predictions at all. The majority of the alpha particles did, indeed, pass through the foil with little deflection, which was expected. But a surprising number of particles were deflected at much larger angles than anticipated. Even more astonishing was the fact that some of the particles bounced back almost directly along their incoming paths. These observations suggested that something was very different within the atom, something much more compact and much more powerful than the original model could explain. The large angle deflections in particular were a crucial and baffling result. In the plum pudding model, such deflections would have been impossible because the diffuse positive charge would not have been strong enough or concentrated enough to significantly repel the alpha particles. If the atom were indeed a spread-out mixture of positive and negative charges, the alpha particles should have passed through the gold foil with minimal interaction, experiencing only small deflection due to minor interactions with electrons. Instead, the alpha particles were being repelled by something much more concentrated and dense than the diffuse charge that the plum pudding model suggested. The fact that some particles were reflected back in nearly the same direction indicated that they had encountered a very small but incredibly dense core within the atom that could exert a significant repulsive force. This core, as later theory would reveal, was the atomic nucleus. The scale of the nucleus, however, was also shocking. In this experiment, the alpha particles were not only deflected by this small but dense region, they were deflected at large angles, implying that the nucleus was extremely compact compared to the overall size of the atom. To put it in perspective, the size of the nucleus was found to be around 1,000,000 times smaller than the size of the entire atom. This revelation radically changed the way scientists thought about the atom, suggesting that atoms were not uniform or homogeneous, but instead contained highly concentrated regions of positive charge. In essence, the unexpected results were a dramatic deviation from what was believed to be true about the atom. The behavior of the alpha particles revealed that atoms were made up of a tiny, dense nucleus at the center, with electrons orbiting at much greater distances. This new insight not only challenged the current understanding, but also laid the groundwork for the development of new models of the atom, eventually leading to the creation of the nuclear model. The surprising deflections and reflections of the alpha particles would forever change the course of atomic theory and our understanding of matter itself. Before the groundbreaking results from the alpha particle scattering experiment, the accepted model of the atom was the plum pudding model, first proposed by J.J. Thomson in the early 20th century. This model suggested that atoms were composed of a uniform, positively charged pudding with negatively charged electrons embedded within it, much like the plums in a traditional British pudding. According to this model, the positive charge was spread throughout the entire atom, with the electrons scattered within this positively charged cloud in such a way that the atom remained electrically neutral overall. The plum pudding model had been a significant step forward in understanding atomic structure, but it was based on a rather simplistic idea. It suggested that the positive charge in an atom was diffused, making the atom essentially uniform. This model aligned with the observations available at the time, including the nature of the atom as a whole. However, it failed to account for the new and unexpected data emerging from the experiment involving alpha particles. When the experiment revealed that most of the alpha particles passed through the gold foil with little deflection, it seemed to suggest that most of the atom's mass and charge were spread out and offered minimal resistance. However, the large angle deflections and even the particles bouncing back suggested the existence of something very different at the center of the atom, a much more concentrated and dense core. These results could not be explained by the plum pudding model, which had assumed that the positive charge was spread out across the entire atom. As a result of these surprising findings, a new model of the atom had to be proposed, one that placed a dense, positively charged nucleus at the center of the atom. This nucleus contained most of the atom's mass and positive charge, while the electrons orbited the nucleus at a relatively large distance, occupying the majority of the atom's volume. The nucleus itself was incredibly small compared to the size of the atom, with a diameter roughly 1,0,0,0,0 times smaller than that of the entire atom. This radically new concept of atomic structure was revolutionary and marked a major shift in how scientists understood the nature of matter. This model, which is now referred to as the nuclear model of the atom, described the atom as being mostly empty space, with a majority of the atom's mass concentrated in the tiny, dense nucleus. The electrons, which were far lighter than the protons and neutrons making up the nucleus, orbited around this central nucleus in well-defined orbits, separated by vast distances in comparison to the size of the nucleus itself. The nuclear model also introduced the concept of atomic stability in a way that the previous model couldn't. By proposing that the positive charge was concentrated in the nucleus, the model explained how the electrostatic repulsion between the negatively charged electrons and the positively charged nucleus could be balanced in such a way that the electrons remained in stable orbits. Furthermore, the idea of a dense nucleus provided a way to explain the powerful forces at work within the atom, especially when looking at how particles interacted with the nucleus, such as in nuclear reactions and other phenomena like radioactive decay. This redefined atomic model did away with the idea of a homogeneous, spread-out atom and replaced it with a more structured, dynamic, and organized picture of the atom's internal makeup. The discovery of the nucleus, its mass, and its positive charge became fundamental to the development of later theories in physics, including the Bohr model of the atom and, eventually, the quantum mechanical model of the atom. In short, the unexpected results of the alpha particle scattering experiment necessitated a complete re-evaluation of the model of the atom. The insight gained from these results helped scientists transition from a simplistic, homogeneous view of the atom to a more accurate understanding of its complex and organized structure, which remains foundational to modern physics and chemistry. The discovery of the nucleus, as revealed by the results of the alpha particle scattering experiment, fundamentally transformed our understanding of atomic structure. Prior to this experiment, scientists had a general idea of the atom's existence, but the exact nature of its internal structure remained largely speculative. The prevailing plum pudding model of the atom, proposed by J.J. Thomson, suggested that the atom was a uniform sphere of positive charge with negatively charged electrons embedded within it, much like plums in a pudding. According to this model, the atom was considered to be a diffuse, evenly distributed entity with no concentrated region of mass or charge. However, the experimental results, which show that a small percentage of alpha particles were deflected at large angles, suggested the presence of something much more concentrated at the center of the atom. Some of the alpha particles even bounced straight back, which indicated that they were being repelled by a very small but dense area within the atom. This unexpected behavior of the alpha particles could not be explained by the existing model. It was clear that the atom had a structure much more intricate than anyone had imagined. The only logical explanation for the scattering patterns was the existence of a dense, positively charged core within the atom. This core, which would later be known as the nucleus, had to be small in size but powerful enough to cause the large angle deflections observed in the experiment. The alpha particles, which themselves carry a positive charge, were repelled by this dense, positively charged region in the center of the atom. This suggested that the nucleus must contain most of the atom's mass and all of its positive charge, while the surrounding empty space held the much lighter electrons. The discovery of the nucleus dramatically changed the way scientists viewed the atom. Prior to this, the atom was thought to be a more or less homogeneous object, with the positive charge distributed throughout the atom. The idea that most of the atom's mass was concentrated in a tiny central nucleus was a revelation. It was soon realized that the nucleus contained not only positively charged protons, but also neutrons, particles with no charge but a similar mass to protons. This insight was crucial in understanding the atom's stability and the forces that held it together. The size of the nucleus was another surprising aspect of this discovery. The experiment revealed that the nucleus was incredibly small, about 1,000,000 times smaller than the overall size of the atom. This meant that the vast majority of the atom was empty space, with electrons orbiting far away from the nucleus in what we now understand as electron shells or orbitals. This finding contradicted earlier models that portrayed atoms as solid, indivisible objects. Instead, it became clear that atoms were largely composed of empty space, with a highly concentrated and dense core at the center. Moreover, the discovery of the nucleus also raised new questions about the nature of atomic interactions. If the nucleus contained the atom's positive charge, it suggested that there was a strong electrostatic force at play between the protons in the nucleus and the electrons orbiting outside. This electrostatic force, along with other forces like the nuclear force, would later play crucial roles in explaining atomic behavior and reactions, including the mechanisms behind radioactive decay, fission, and fusion. The discovery of the nucleus also had profound implications for nuclear physics. It laid the foundation for the understanding of nuclear reactions, where the nucleus is involved in processes like fission, the splitting of atomic nuclei, and fusion, the joining of atomic nuclei. These discoveries not only reshaped the way scientists viewed matter at the atomic level, but also led to revolutionary advancements in energy production, medicine, and even weapons technology. In summary, the discovery of the nucleus was one of the most important revelations in the history of science. It shifted our understanding of the atom from a simplistic, diffuse entity to a much more complex and structured system with a tiny, dense core at its center. This discovery led to the development of more sophisticated atomic models, including Bohr's model of the atom and the quantum mechanical model, and paved the way for countless advancements in physics, chemistry, and technology. The nucleus remains a key concept in modern science, and our understanding of it continues to evolve as we explore the mysteries of atomic and subatomic particles. The concept of nuclear force emerged as a critical explanation for the stability of atomic nuclei, marking a significant shift in our understanding of the forces that govern atomic structure. Prior to the discovery of the nucleus and the advent of nuclear physics, the behavior of particles within atoms was largely explained by classical forces, such as electromagnetism. However, these conventional forces could not fully account for the interactions that held the nucleus together. The repulsive electrostatic force between the positively charged protons in the nucleus, for instance, would naturally push them apart rather than keeping them bound together. This paradox led to the necessity of a new type of force, what we now call the nuclear force, which plays a pivotal role in maintaining the stability of atomic nuclei. The role of the nuclear force in holding nuclei together. The nuclear force, also known as the strong force or strong nuclear interaction, is the force responsible for holding protons and neutrons together in the atomic nucleus. The strong force is unique in that it acts over very short distances, on the order of a femtometer, 10 to the power of 15 meters, which is roughly the size of an atomic nucleus. At these tiny scales, the strong force is incredibly powerful, far stronger than the electromagnetic force that causes like charges to repel. While protons, being positively charged, would naturally repel each other due to the electrostatic force, the nuclear force is able to overcome this repulsion at short distances. The strong force binds protons and neutrons together, ensuring that the nucleus remains intact despite the powerful repulsive forces between positively charged protons. Without the nuclear force, atomic nuclei would simply not exist in their current stable form, and atoms would disintegrate due to the inability of protons to stay clustered together. The strong force between protons and neutrons, the strong nuclear force, is not only responsible for holding protons together, but also plays a key role in binding neutrons within the nucleus. Neutrons, which have no charge, experience the nuclear force just like protons, allowing them to be held together in close proximity within the nucleus. This force is much stronger than the electromagnetic repulsion between protons, but it operates only over short distances. As the distance between nucleons, protons and neutrons, increases, the nuclear force weakens rapidly. Interestingly, while protons repel each other due to their positive charge, the presence of neutrons helps to further stabilize the nucleus by providing an additional source of attractive nuclear force. Neutrons, by not carrying a charge, do not contribute to electrostatic repulsion, but they experience the strong nuclear force just like protons. This means that in nuclei with many protons, the neutrons play an essential role in keeping the nucleus stable by reducing the net repulsion between protons and helping to mediate the strong force between all nucleons. The range and strength of the nuclear force is incredibly short, but also very short-ranged. At distances of less than about 1 to 2 femtometers, the force is attractive, and nucleons are bound tightly together. However, if nucleons are separated by larger distances, the strong force rapidly diminishes in strength and eventually becomes negligible. This short-range nature of the force is one reason why atomic nuclei are so small compared to the overall size of an atom, which is mostly empty space occupied by electrons. At distances much greater than the range of the nuclear force, the electromagnetic force takes over, with protons repelling each other because of their like positive charges. The fact that the strong force is so short-ranged is also why atomic nuclei are confined to such tiny volumes compared to the space that electrons occupy in an atom. This interaction governs the behavior of the nucleus, ensuring that it remains compact and stable. The strong force and its impact on nuclear reactions. The concept of the nuclear force also provides the foundation for understanding nuclear reactions, such as nuclear fission and nuclear fusion. In nuclear fission, the nucleus of a heavy element like uranium is split into 2 or more smaller nuclei, releasing vast amounts of energy. The strong nuclear force plays a key role in this process, as it holds the nucleus together until the force of an external particle, or neutron, causes the nucleus to break apart, overcoming the attractive force that binds it. In nuclear fusion, which powers the sun and other stars, light nuclei such as hydrogen combine to form a heavier nucleus, like helium. The nuclear force is responsible for the attraction between nucleons that allows the fusion process to occur at extremely high temperatures and pressures, as the nuclei must come close enough for the strong force to take effect. This is why fusion reactions require such high energy to overcome the electrostatic repulsion between positively charged nuclei. Nuclear force and the stability of elements. The balance between the electromagnetic force, which tends to push protons apart, and the nuclear force, which holds the nucleus together, is critical to the stability of atomic nuclei. If there were not enough neutrons to mediate the strong force and balance the electromagnetic repulsion between protons, nuclei would be unstable and prone to disintegration. Conversely, too many neutrons can lead to instability, resulting in radioactive decay or fission. The interplay between these forces dictates the creation and stability of elements in the universe. For example, heavier elements like uranium or thorium require a higher ratio of neutrons to protons to maintain stability due to the increased electromagnetic repulsion between more protons. On the other hand, lighter elements, such as hydrogen or helium, have a more balanced ratio, resulting in a stable atomic structure. The discovery of the nucleus and the revelation of the nuclear force fundamentally altered the way scientists thought about the structure of the atom. Prior to these discoveries, the prevailing idea of the atom was a relatively simplistic and diffuse model, most notably represented by J.J. Thomson's plum pudding model. According to this model, the atom was envisioned as a sphere of positively charged matter, with negatively charged electrons embedded in it, much like raisins scattered throughout a pudding. This model, while groundbreaking at the time, was later found to be inadequate in explaining the complex phenomena observed in experiments, particularly the scattering of alpha particles. Once the results of the alpha particle scattering experiment revealed the existence of a small, dense nucleus at the center of the atom, scientists were forced to rethink their entire understanding of atomic structure. The implications were profound. The atom was no longer viewed as a simple, homogeneous entity. Instead, it was recognized as a complex system with a highly organized structure, a dense nucleus containing protons and neutrons, surrounded by a cloud of electrons that orbited the nucleus at a considerable distance. The shift from the plum pudding model, the existing plum pudding model, in which the positive charge was assumed to be spread out across the entire atom, could not account for the experimental results. The unexpected large-angle deflections of alpha particles indicated that the positive charge was concentrated in a very small, dense region at the center of the atom, rather than being diffused across the entire atom. This required a radical shift in how scientists envisioned atomic structure. The new model was soon proposed, which is now known as the nuclear model of the atom. In this model, most of the atom's mass and positive charge were concentrated in a tiny, dense core, the nucleus, and the electrons orbited this nucleus at relatively large distances. The nucleus itself was incredibly small in comparison to the entire atom, and its size was on the order of 1,000,000 times smaller than the atom as a whole. This realization marked the beginning of a new understanding of atomic structure, where atoms were recognized as mostly empty space with a central, dense nucleus. The concept of atomic size and empty space. The new model of the atom also led to a re-evaluation of the atom's size. Previously, it had been thought that atoms were relatively solid objects, with a uniform distribution of charge and mass. However, with the discovery of the nucleus and its small size in relation to the atom, scientists realized that atoms are, for the most part, empty space. The majority of an atom's volume is taken up by the electron cloud that surrounds the nucleus, which is mostly empty space in which the electrons move. The electrons, which are much lighter than protons and neutrons, occupy discrete energy levels, or orbitals, around the nucleus. This new understanding of the atom structure helped to clarify the behavior of atomic interactions and chemical bonding. For example, it was now clear that chemical reactions are largely driven by the interaction of electrons in the outermost shells of atoms, rather than the interaction of the more massive protons and neutrons in the nucleus. This led to a greater understanding of atomic properties such as ionization energy, electronegativity, and atomic radius, all of which depend on the configuration and behavior of electrons around the nucleus. The development of new atomic models. The nuclear model, while revolutionary, was not the final word in atomic theory. The discovery of the nucleus paved the way for even more advanced models, as scientists sought to explain the behavior of electrons within atoms. In 1913, Niels Bohr introduced his atomic model, which built upon the nuclear model but introduced the idea of quantized orbits for electrons around the nucleus. According to Bohr's model, electrons orbit the nucleus in specific, fixed orbits or energy levels. Electrons could only occupy these levels and could jumping from one orbit to another. This model successfully explained the spectral lines of hydrogen and was an important step toward modern quantum theory. However, Bohr's model had limitations. It could not fully explain the behavior of atoms with more than one electron, nor could it account for the complex behavior of electrons in multi-electron atoms. This led to the development of quantum mechanics, which describes the behavior of electrons not as particles moving in fixed orbits, but as waves spread out in probability clouds called orbitals. The Schrödinger equation and the Heisenberg uncertainty principle became fundamental tools for understanding the behavior of electrons at atomic scales. The emergence of quantum mechanics. With the development of quantum mechanics, scientists began to move away from the idea of definite orbits for electrons and instead embraced the idea of electron clouds or orbitals, which describe the probability of finding an electron in a certain region of space around the nucleus. This marked a further departure from the classical concept of fixed, well-defined orbits. Quantum mechanics introduced the idea that electrons do not have precise positions or velocities, but rather exist in states of probability, governed by wave functions. Moreover, the structure of the nucleus itself became a topic of intense study. The discovery that the nucleus contained protons and neutrons, the latter discovered by James Chadwick in 1932, led to a deeper understanding of nuclear reactions, nuclear decay, and the forces that govern subatomic particles. The interplay between the electromagnetic force, which repels like charges, and the strong nuclear force, which binds protons and neutrons together, was found to play a crucial role in the stability and behavior of atomic nuclei. The study of nuclear interactions and subatomic particles eventually led to the field of particle physics, which continues to explore the fundamental components of matter. Modern atomic theory today, the understanding of atomic structure, is far more sophisticated than it was in the early 20th century. The model of the atom has evolved from a simple, uniform entity to a complex system composed of a tiny, dense nucleus surrounded by a cloud of electrons and orbitals. Quantum mechanics provides the foundation for understanding how electrons behave in atoms and molecules, explaining everything from the structure of the periodic table to the behavior of light in chemical reactions. In conclusion, the discovery of the nucleus and the subsequent shift to the nuclear model of the atom forced a complete re-evaluation of atomic structure. The atom was no longer seen as a uniform sphere of matter, but as a complex dynamic system with a tiny nucleus at its center, surrounded by electrons that occupied discrete energy levels. This new understanding laid the foundation for the development of modern quantum theory, which continues to shape our understanding of the atomic world today. The discovery of the nucleus and the subsequent re-evaluation of atomic structure had a profound and lasting impact on the development of modern physics. It not only revolutionized our understanding of the atom, but also paved the way for numerous groundbreaking advancements in the field. The concept of a dense, positively charged nucleus at the center of the atom, surrounded by electrons, became a cornerstone of the study of matter at the microscopic level. The subsequent developments in quantum mechanics, nuclear physics, and particle physics were all directly influenced by this newfound understanding of atomic structure, revolutionizing atomic and nuclear theory. The most immediate impact of the discovery of the nucleus was on atomic and nuclear theory. Prior to the discovery, the plum pudding model of the atom, proposed by J.J. Thomson, dominated scientific thought. This model assumed that the positive charge in an atom was spread out uniformly, with electrons embedded like raisins within the positive charge. However, the revelation that most of the atom's mass was concentrated in a tiny, dense nucleus, surrounded by largely empty space, was a radical departure from this view. This new understanding necessitated the creation of new models of atomic structure, most notably the nuclear model introduced by Ernest Rutherford, which formed the foundation for future atomic theories. In particular, the discovery of the nucleus spurred further developments in nuclear physics. The realization that the atom's mass and positive charge were concentrated in the nucleus led to the study of nuclear reactions, nuclear forces, and the forces that bind protons and neutrons together in the nucleus. Understanding the nuclear force, a force that is stronger than the electromagnetic force but acts only at very short distances, became central to understanding atomic stability and the reactions that occur within the nucleus, such as nuclear fission and nuclear fusion. These concepts not only explained the behavior of certain elements but also laid the groundwork for the development of nuclear energy, both in terms of its peaceful applications and its role in atomic weaponry. The birth of quantum mechanics. Perhaps the most significant consequence of rethinking atomic structure was the development of quantum mechanics. The discovery of the nucleus and the concept of a tiny, dense central core within atoms challenged classical physics and prompted physicists to search for a more comprehensive theory to explain atomic behavior. Classical Newtonian mechanics could not explain the behavior of electrons in atoms, particularly the quantized energy levels observed in atomic spectra. This led to the development of quantum mechanics, which fundamentally changed the way we view particles and their interactions. The work of scientists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger provided new insights into the behavior of particles at atomic and subatomic scales. Bohr's model of the atom, which incorporated discrete energy levels for electrons, was an early step toward the quantum theory. It was later expanded upon by Schrödinger's wave mechanics and Heisenberg's uncertainty principle, which described the behavior of particles as probabilistic rather than deterministic. This was a departure from the classical view of particles as having fixed positions and velocities. Quantum mechanics, which views electrons as existing in orbitals or probability clouds rather than fixed orbits, revolutionized our understanding of atomic interactions and chemical bonding. The advent of quantum mechanics also laid the foundation for the study of quantum field theory, which provides a framework for understanding the interactions between particles and fields, including the forces that govern the universe. Quantum electrodynamics, QED, and quantum chromodynamics, QCD, are two key aspects of this theory that describe the behavior of electromagnetic and strong nuclear forces, respectively. Advancements in particle physics. The discovery of the nucleus also had a profound impact on the field of particle physics, the branch of physics concerned with the study of the fundamental particles of nature. Once the nucleus was identified as the central core of the atom, scientists turned their attention to the particles within the nucleus, protons and neutrons, as well as the forces acting between them. In the mid-20th century, the study of nuclear reactions and the forces that govern particle interactions led to the discovery of additional subatomic particles, such as the neutron, discovered by James Chadwick in 1932, and the quark, proposed by Murray Gell-Mann and George Zweig in the 1960s. The concept of quarks, elementary particles that combine to form protons and neutrons, led to a deeper understanding of the internal structure of matter. This idea became a key component of the Standard Model of particle physics, which describes all known elementary particles and their interactions. The exploration of subatomic particles also led to the development of particle accelerators, large machines that accelerate particles to extremely high speeds and smash them together to observe their interactions. These accelerators have been crucial in uncovering the properties of fundamental particles and understanding the forces that govern their behavior. The discovery of the Higgs boson at CERN in 2012, a particle that gives mass to other particles, was one of the most significant achievements in particle physics, and is directly tied to the principles of quantum mechanics and the understanding of the atomic structure. Nuclear energy and medicine. The advancements in nuclear physics that followed the discovery of the nucleus have had practical implications across a wide range of fields, most notably in nuclear energy and medicine. The understanding of nuclear reactions, particularly fission and fusion, has led to the development of nuclear power plants, which provide a significant portion of the world's electricity. These plants harness the energy released when atomic nuclei undergo fission, splitting into smaller nuclei, releasing enormous amounts of energy in the process. In medicine, nuclear physics has led to the development of radiation therapy for treating cancer, as well as diagnostic techniques like PET scans, positron emission tomography, and CT scans, computed tomography, which use nuclear technology to visualize internal body structures. The study of radioisotopes and their interactions with matter has been instrumental in both therapeutic and diagnostic applications, improving the effectiveness of medical treatments and enabling early detection of diseases. The Big Bang Theory and cosmology. The discovery of the nucleus and the subsequent advancements in our understanding of atomic and nuclear interactions also had significant implications for cosmology and the study of the universe's origins. Understanding the processes that occur inside stars, such as nuclear fusion, has allowed scientists to develop models of how stars and galaxies form and evolve. These processes are responsible for the creation of elements in the universe, a phenomenon known as nucleosynthesis. The study of these processes has been crucial in developing the Big Bang Theory, which proposes that the universe began as a hot, dense state and has been expanding ever since. By examining the behavior of atoms, isotopes, and nuclei, scientists have been able to track the formation of the universe's elements and better understand the processes that govern the early stages of the cosmos. This has provided important insights into the formation of galaxies, stars, and planets, as well as the ongoing evolution of the universe itself. As we draw to the close of our discussion, we can appreciate the immense impact that the discovery of the atomic nucleus has had on the world of science and beyond. What began as a series of experiments questioning the very nature of the atom has evolved into a revolution that transformed not only our understanding of the smallest building blocks of matter, but also our ability to shape the future of technology, medicine, and even the universe itself. The realization that atoms consist of a dense nucleus surrounded by electrons gave rise to groundbreaking theories in nuclear physics, quantum mechanics, and particle physics. These developments reshaped our entire view of the cosmos, from the formation of stars to the behavior of the tiniest subatomic particles. The advances we've witnessed in energy production, medical diagnostics, and treatments, along with our deeper understanding of the universe's origins, all trace their roots to this pivotal discovery. But perhaps the most important lesson we can take away from this journey is the idea that science is ever evolving. The questions we ask today will fuel the discoveries of tomorrow. What was once a mystery is now a foundation on which countless future breakthroughs will be built. The study of atomic and subatomic particles has opened a door to infinite possibilities, and it is up to us to continue exploring and pushing the boundaries of what we know. In closing, let us remember that the curiosity, ingenuity, and perseverance that drove these discoveries are qualities that continue to inspire progress in every field. The future is bright, and as we stand on the shoulders of giants, the journey ahead promises even more profound revelations about the nature of our world and beyond. Thank you.